Okay, welcome back to the live stream. So last week we added void and unsigned types, which allowed us to slowly move toward a fully fledged type system. But one important thing that is missing is implicit and also explicit conversions. So for example, in this program, we're getting two errors. The first one is here because we're subtracting 1 from n, but n is an unsigned int and 1 is a signed int. So that's an error because we do not do any implicit conversions at the moment. And the second one is here when we call it, so 35, same issue, it's not an unsigned int. So we're getting an error. And the plan for this stream is to fix those errors. So to allow implicit conversions. And the way we're doing that is in two steps. So an implicit conversion is just a cast that is automatically inserted by the compiler in the appropriate places. So the first thing that we're actually going to do is implement casts and then do the backend stuff. And then when we do implicit conversions, all we need to do is just insert the casts appropriately. So casts. The C standard defines them here. So a cast operator is like a type name in parentheses, and then like the expression that is being casted. And there are some constraints, so it should be a scalar type or void. Then there's something about pointers that we don't care about because we don't have pointers at the moment, likewise for floating points. And then it simply converts the value of the expression to that type. And then, yeah, and then it does that somehow. Yeah. So I'm curious what it actually like defines. Defines what the cast does, like in the backend. Yeah, I mean, we know what it does, so okay. So that's a cast. I'm interested the grammar protection for type name. What is that? Because we are currently been dealing with type specifiers, and those aren't type names. So let me check in the grammar where we got type names. So we need to pass a type name. So when we got the cast expression, that is also uses type name. Where do we like type specifier qualifier, type qualifier, type name. A specifier qualifier list followed by an abstract declarator, which is optional. So the abstract declarator part, this takes care of pointers, and then the specifier qualifier list. I'm assuming that is like it's a type specifier. It's a list of type specifiers and then optional attributes. We are not worrying about attributes at the moment, so a list of type specifier or qualifier, this is a type specifier. Do we specify a type? Which is a type specifier, a type qualifier, or alignment specifier. What's a type qualifier? Yeah, right, the qualifiers and then alignment. Okay, so we're not worrying about qualifiers or alignment at the moment, so a type specifier qualifier is just a list of type specifiers. And then what was a type name? This was this weird specifier qualifier list, so just a list of type specifiers. We already figured that out. And then a type name is just specifiers abstract declarator. Okay, so let's actually start writing the grammar production first, because we just looked at it. So somewhere in the expression, we want to pass a cast expression. So let's just write the type name production here. So type name. And then a type name is a list of specifier qualifiers followed by an abstract declarator. So when we pass declaration, we are passing type specifier. Right. So we want to pass this production. So I'm guessing this is more arguably should be called type specifier list because it's multiple type specifiers and not just one. So type name Then we want type specifier list. So we're parsing a list type specifier followed by an optional abstract declarator. Yeah, so that is a declarator. So we want to pass an abstract one. I wonder whether I should be able to do that. So type name, and then we want declarator, and then we are parsing. C, I can do that because I can. Is that a branch actually? Yeah, no, it's not a branch. Because, okay. So we want to pass an optional abstract declarator, but an abstract declarator by itself okay, you know what? Since the declarator part only takes care of like casting to pointers and stuff, and we don't have pointers at the moment anyway, let's just not bother with it. So we're only having simple types anyway, so let's worry about that at some later point. So type name, and then we are simply forwarding, right? Because the type specifier list, this gives us a type. So we're simply forwarding that type. Great. And now we can pass a cast. So a cast expression is like between unary and multiplicative from the precedence here. So here we've got a cast. This is like a cast is some sort of prefix operator, where the operator is, we need to specify some sort of type here. So the operator is a type. So like this is it's a prefix operator, where this is like the operator part, and then this is the expression. So the operator is a DSL parenthesized type name. And then the operand is a postfix expression. No, it's actually a unary expression. So right here. So the operand is a unary expression. And then in the multiplicative group, the operand now here is a cast. Okay. So that's that. And then we got an overload that looks something like this. So we take the operator tag, and then we've got a type, which is like the target type, and then we've got an expression, which is a chart. Okay. And now what we want to do is we want to create an S node. So let's finally add the S node. So we've got expression, list of expression, integer constant, identifier, function call. Let's add them here. A cast expression or implicit conversion. So, because implicit conversion just inserts cast in the proper places. So this is a basic node inheriting from expression. And then it basically has the type as its member, and it can be constructed using the target type and the expression. How do I call it here? So this is the child here. Child, and then node base takes the constructor. And so we know the type of the cast expression, which is always the target type. And I'm guessing we don't need to store it then, because like a cast expression is uniquely determined by the type. And then we just insert the child. child. Great. Now we need to add that here. Cast expression. Need to insert that here. So when we're printing it, we want a cast expression. Cast expression. And then when we want to finally print it, we move over here, have a cast expression. Expression. Hang on, what am I doing? So essentially just want to print the type. So let's just say just print the type. So dump type. Okay. So this part should compile. Except that we need to do it. Okay. So what we're then creating here is simply cast nodes, cast expression at the location of the operator, given the target type and the child. And this is recast. Of course, we don't have this one. Okay. And now it should work. So it compiles. We should be able to do something like unsigned 35. Right. And then right here, we should be able to say unsigned 1. Let's say use unsigned int, just so we can see that works. So we're getting an AST. We're getting no type errors because we now have the appropriate type. So we've got in the function decal right here, we've gotten the cast expression to un64 of the integer constant expression. So that's good. Of course, we need to add them to CodeGen. Right now, it doesn't do any CodeGen, which is fine because at the hardware level, there's no difference between an int and an unsigned int, so the cast doesn't actually need to do any assembly code, but we should still handle it properly once we add more types. So where do we handle unary expressions? Above, we handle conversions. So after we visited the child, we want to convert the cast expression. At this point, the value to be casted is on top of the stack. And now we need to do a bunch of things based on the exact type of both the source and the destination. Right. So, right now it's trivial because we are only having two cases. So let's iterate over the first. We switch over the sort of type family of the target. So if we are having the type void, then a cast void simply discards the value. We do that by popping the value on top of the stack. Otherwise, if we want to cast to an unsigned integer, then we need to look at the source family. And right now, the only other sort of type family that is allowed here is a signed integer. So let's just say it's signed int mission type. And then we want to convert the unsigned int, the signed int. So the child expression. So the type of the child expression has to be signed, and we need a getter for that. So getter for child. So the child has to be a signed int, and the target is an unsigned int, and then we want to convert a signed int to an unsigned int. And this is technically an OOP, but Lauf provides built-in that we should call in case it is no longer an OOP. So let's just do that. So we want to convert now lib int signed to unsigned, right? And then we need to specify what happens on overflow. So I guess it is not quite a no. So where does the standard says? If the value of the expression is represented with greater range of precision, right? So just removes. What did it say here? Ah, right. I'm guessing like this specifies. Okay. So the target types. So the somewhere it says that right, here it says so signed and unsigned integer. The new type is unsigned. The value is converted by repeatedly adding or subtracting one more than the maximum value that can be represented in the new type until the value is in the range of the new type. Okay, so I believe this is just the standardese saying for it wraps around. Because, I mean, that's what it does. So lib int overflow wrap. So when we got a negative, right. So unsigned, so we got an unsigned int which can store more positive values than the int can store negatives. And what we need to do is then, if you have a negative value, we repeatedly add until we reach, we wrap around. Okay, so that. And then the other case, if the target is a signed int, if the target is a signed int and the value cannot be represented, then the result is implementation defined or signal fetch. So what my implementation is going to do is panic on overflow. So we know that the other type has to be unsigned int, call built-in int signed to unsigned to signed, and here we want to panic. Okay, else unreachable. Now other conversion is allowed. Okay. So nothing should have changed because this is an OOP. And we even, so for example, we are doing a signed unsigned conversion here for the 1. But since 1 is a constant, like this has been completely folded at compile time. So to actually see that we are doing something, we have to do like convert -1 to unsigned int. So now we are getting a cast expression of -1, which means that here we are getting an integer overflow error, which is what we wanted. Because -1 converted. Wait, why are we getting? No, that's not right actually. Oh, okay. So we have a couple of bugs. So the issue is that for some reason Ninja is rebuilding everything at the moment. I have to look into that. So we're getting when we generate the arithmetic operations, when we convert the -1, so when we convert the -1, we creating a panic even though we should wrap around because we are not creating the correct. So currently overflow of unsigned integers creates a panic instead of wrapping, so that is wrong. That we have to fix that later. But anyways, so the casts work, but we need to do a bit of type checking. So for the cast expression, we need a scalar type or void. So if not, so if this is a scalar type or a void type, then we create an error. Invalid target type for cast at the location, and then we cast it here. Okay. So when we do something like we don't have a type that will trigger this, because we're only having scalar type and void at the moment, so we can't test that diagnostic. What else? Conversion that involve pointers. No, not our deal. I'm guessing like there are some source type, right? If the source type isn't so we have to like, right. Conversions only between arithmetic operands and void and pointers. So we have to do some sort of constraint on the source type. So this check that the target type is valid. And then here check that we can convert the source type to target type. So if the target type is void, then all source types allowed to do nothing. I like that sort of where we do an if and the body is a comment. Else if the target type is arithmetic, we are having all of the rules in this operand. The list in 6318. All right. And then we're having these operands. So we don't have L values, errors, and function designators. The cast to void can do anything, and we don't having pointers, so we don't have to worry about those cases. So in the case of the arithmetic operands, currently I believe we can essentially convert any arithmetic operand to any other arithmetic operand. So we just need to assert that the starting with an arithmetic operand. So if the type of the expression is not arithmetic, then we issue an error. Invalid source type for cast. Okay. So we can test that error by attempting to cast void to int. So the cast void to int is not allowed, and we're getting an error about the invalid source type. Okay, the error highlighting could be better, but I'm not bothering with that right now. Okay, and finally, note that the codegen, we are assuming that the types aren't the same when we generate a cast. And this makes sense, because the standard even says that somewhere, I believe here, I read that. A cast that specifies no conversion has no effect. Right? So if we are building a cast where we're having the same type already, so the target type and the child type, then we can simply return the child type, right? Because we don't need to do anything to do that cast. Okay. Where I'm getting a cryptic error. Must match previous return type. Wow. I've never seen that error. Okay. So that should be explicit casts for our limited set of types that we're currently having. Okay. I still want to see, like, generate some overflow for So I want to generate like an overflow by converting an unsigned int to a signed int. So I want to do int. So we've got, this is a 64-bit, so we're having 64-bit unsigned integer, and we're converting them to a signed integer, and this is an integer overflow, so we should get a panic. Yeah, we're getting a panic, that we're having an integer overflow caused by the call here. So this pushes pushes the one that has all bits set, so negated 0, and then it converts them to a signed, and this panics. Right, so this is exactly line 17. Okay, great. So let's commit that. How do I use the interface net? Add cast expression. Good. So then I noticed that we're having a bug. So let's fix that really quick. So when we do like a -1, this panics, even though it should wrap around. So this panics, it really shouldn't. And the reason for that is that here in CodeGen, for unsigned types, we want overflow wrap, not panic. And the rest can't overflow. So now we're getting like I would say we're getting an infinite loop, but this is a stack overflow. So we're getting like fitting about 50,000 stack frames before the memory limit of the VM is reached. Okay, because we're obviously adding a bunch here. Okay. Fix overflow behavior of unsigned operations. Great. So now let's implement implicit conversions. And as I've hinted, the way we're doing implicit conversions is by simply adding cast expression nodes in the appropriate places. So what are implicit conversions? In C, it is quite a bit nicer. So what we are, there are essentially two that we need to worry about right now. There are a bunch more in C++, so thank God we're not writing a C++ compiler. The first one is that a bunch of places, for example, this one here, integer promotions are performed. And what this means is, so in C, when we do arithmetic, on types that are smaller than int, they are automatically, so if we are writing something like short a and b, and then we're writing short c equal a plus b. We are not actually adding two shorts, we are adding two ints. So C has no arithmetic on types smaller than int. And so what's going on here is that every time essentially we look at a type that is smaller than an int, it is automatically promoted to int, or unsigned int, depending on some rules. So this is called integer promotion. We at the moment don't have any type smaller than int, so this is not an issue right now. What we do need to take care about is what's called for example, during assignment, we want to assign int to unsigned. And the left operand, where does it say? And then if it overlaps, I mean, like so if the type aren't the same, it converts them, and it says it somewhere. Left operand has atomic arithmetic type. So this is the thing. After would have after L value conversion is not relevant. Something about overlapping. Right here. It's converted to the type of the assignment expression. Yeah, so this we need to do a conversion here. So let's actually start right there. So when we do assignment, we're doing assignment right here. It tells it to do conversion. So we need to do more type checks here. Right, to do type check. Okay, so we need to convert them. So we need to convert the right operand to the type of the left operand. And so let's add a helper function to do a conversion, because we need to do that a bunch of times. Let's call this an assignment conversion, because we're having because here it is clear that we're converting the right type to the left type. When we do like an addition, we're converting both to some sort of common type. But here not, so let's call this an assignment conversion. So we are having like helper functions somewhere here on the top. Set new decal, check inside loop. Yeah, let's just write one here. Expression do assignment conversion. Target type so, and then we're getting the state. So attempt to convert the value expression to target type by creating a cast expression or raising an error. Okay, so if we are already having the type, the correct type, then we don't need to do anything. So is same the target type and the type of the value, then we don't need to do anything and can just return value. Otherwise, we need to check essentially whether a conversion is allowed. And this is the exact same logic that we implemented here for the cast. Right here? No, not right here in the appropriate lambda callback. Here. So this logic, we need to check whether we convert the child type to the target type. So let's add a helper function. Let's add it to the AST, because this might be useful during backend coding as well. So bool, and there's a C++ type thread that does exactly that. It's called a convertible, I think. Is convertible. Checks, yeah, for implicit conversions. So is convertible type from const type true. So is convertible where was I? Right here. So this logic, if 2 is void, then it's true. Yeah. Or nah, that's not the exact same logic, because the cast checks for whether an explicit conversion is allowed, and we want to check whether an implicit conversion is allowed. So never mind that. where does it say? I believe like the only implicit conversion is like involve the usual arithmetic conversions, right? C doesn't. What exactly is allowed in sort of implicit conversions on assignment? Like where does it say? Like you can convert something to void, but like this isn't an implicit conversion that's allowed. Like if you do if we do return 42, that's an error because we cannot implicitly convert 42 to void. So that is not an implicit conversions, but it says here doesn't specify. So the writer is converted, right? So where does it say? Okay, I have to look at the standard later to figure out where this is actually specified. So right now I know that we can convert unsigned to signed and vice versa. So let's just implement my knowledge of C instead of actual C. Okay, so if is arithmetic target type, like we can do between any sort of like real and floating point types, we can do any sort of conversion between them. I know that. Like there are some compilers issue warnings for certain, but we're not bothering with them. So we allow all sorts of implicit conversions here, and then do that more properly. So if both are arithmetic types, then we can do definitely can do a conversion. So what we want is we want to create a new cast expression. So this has like a synthesized location. So the log is the location of, let's say, the value. Location of the value. Right, synthesized this, both are not. Okay. So location and then target type value. To do this is done from memory. Find the place in the spec where implicit conversions are specified. And we haven't reached that one, then we issue a diagnostic. Cannot do implicit conversion. Cannot do implicit conversion in assignment. Actually, let's use the location of the also for the cast. And then we simply return. Okay. So we issue an error if we reach this point, and then we return the value unchanged. And this is because, like, after we issue an error, like the invariance of the as don't matter. So we just continue on pretending this worked fine. And then assignment up. So somewhere here. What we are doing is right is now do assignment conversion state location left type right. So we convert the right type to the appropriate type if necessary, issue an error if that isn't the case, and so on. And so now when we go to our file, we should, I guess we don't have an assignment anymore to test. So let's do int I 42 unsigned. And I mean, that worked. So, right, it would previously cause an error and now it doesn't. So we are doing assignment conversions. So the next thing is when we do a function call, then we also want conversions. So now we need to do right here. So we currently, right. Oh, this is, we can't actually do that. Like the idea is we could just do assignment conversion and update the argument if necessary, but we can't actually modify the node within the iteration. So we have to do a bit more cheeky. Oh, that is actually a bit annoying. So we want to, like, this is expression list as an intrinsically linked list, and we want to sort of like replace a node. But we can't do that. This is actually tricky to implement. Right, so we can't modify the node while it is in this list, and we can't like do an implicit conversion with that while it is in there. I can't actually implement that without doing a feature in Dryad first. So I need some way to like remove a node from this list. Like I need a new function for that. Before, at a minimum, and then I need to rebuild that list containing the new child nodes. That is really annoying. Okay, so I want to remove a node and then later replace it with a new one. At like in the same position. But for now, let's just add a function to remove a node. So let's call this one sort of like does standard list has remove function? I think it does, but it does something different. I think. Oh no, it has remove. Removes all elements that are equal to value. Which I guess, yeah. So remove a node. So we want to remove a node. This is done by, so this is a linked list. Set the next sibling to right, we need the previous one. This is a single linked list. I can't actually remove nodes from it. That is really annoying. So how do I best solve that? Okay. So let's, instead of an unlinked load list, which is like intrinsically linked, let's just use a vector. And then it works out. Okay, yeah, that's the easiest change. So we've got a vector, and now I can do this hack where we modify the argument now. Oh, this is such an awful hack. So do assignment conversion state as location of argument parent type argument. So we really shouldn't, this is like to do abuse of algorithm. Okay. But like a convenient way to iterate over them in pairs. All right, of course, this is no longer a thing. Insert. Like so, insert after the last child the expression, and then we update that to expression. And this is implicitly. Oh, right, the expression list should be a pointer of expression, not expressions. Okay, that actually seemed to work. I'm surprised it did, to be honest. So let's see, do we actually do like the correct implicit conversion? Nope. Yeah, I don't know why Ninja currently insists on rebuilding everything all the time. Why is this linked in tree? Oh, right, because I actually need to modify argument here. So I should have declared this one, now discard. So now when we're doing the actual call, somewhere in F, we've inserted a cast. And this now works. Okay, great. So horrible implementation, but it works for now. I'll fix it off camera. So I believe those are the only two places where we do the sort of assignment conversion. Let's actually see how bad the error message looks. So we cannot convert void to unsigned int. Cannot do implicit conversion in assignment. Yeah, okay, that's fine. Right, because so what that error message says is like this implicit conversion here doesn't work, and that's fair enough. Okay. At implicit assignment conversion. Implementation is a bit hacky. Need to clean up. Great. So what's the last place is like this. Right, when we do like subtraction and other binary operators, we want implicit conversions here. And this is what's called the usual arithmetic conversions. So the standards right here specifies usual arithmetic conversions. And what they're essentially doing is like whenever we're having two operands, how do we convert them using those rules? This is like the common type equivalent for C. We have to ignore all of those because we don't have any of those types at the moment. So we do integer promotion. This is what I mentioned. We don't have types smaller, so we don't need to do integer promotion. And then we need to implement those rules. And this makes reference to like the rank of an integer type, which is something that we also should implement. Like it's defined here. It's like defines some sort of like partial or total, I don't know, total order maybe, I don't know, of the integer type. So essentially like sort them by size. And like the size of an integer type could be its rank. So let's actually use that as its rank. So the type has a rank, or rather, yeah. Oh, I don't actually need that one. And yeah, right, I can amend. Okay. So unsigned integer rank of returns -1 for non-integers. So Riot node has kind. It's not a built-in type, then it doesn't have a rank. Otherwise, Riot node cast built-in type kind, switch kind. Not an integer, and here we return let's actually use the number of bits, so it's like nice self-documented. Okay, so that is the integer, and then in the usual arithmetic conversions we can essentially implement a similar function now. So in compiler, do assignment conversion, performs the usual arithmetic conversions on both operands. Right, do usual arithmetic conversions, states, and we modify them, so we take them by reference. Okay, so let's implement essentially, if both have the same types, then we do nothing. Same type and the right-hand side have the same type, then we return. Otherwise, both operands have signed integer types or have unsigned integer types converted to the type of the operand with greater rank. Okay. But we are already like we are essentially currently always in this case because we don't have any of the other types. So let's encode that by asserting that we are having integer types. Okay. Okay. So if both are signed or unsigned types, we look at the rank. So if same signedness essentially is signed int type equal to signed int. Yeah, that's type. Then rank ls integer rank of. So we get the rank and we convert to the one with the bigger rank, right? Greater rank. Okay. If rank ls greater rank hs, we convert the right-hand side to the left-hand side. Cast expression. We need a location here. Location block. So convert to the bigger type, which is the type of the left-hand side. Convert right-hand side to type of the left-hand side. Otherwise, we convert the left-hand side to the type of the right-hand side. Okay. The next case. So now we're in a case where one is unsigned and one is signed. So we need to figure out which one that is. So auto signed op. So if the ls is signed, then that is ls, otherwise that is right-hand side, and the unsigned op is the okay. So otherwise, if the operand that has unsigned integer type has rank greater or equal to the rank of the other operand, then the one with signed is converted to unsigned. Okay, so signed rank, the integer rank of the signed operand, And the unsigned rank is the one of the unsigned. And if the unsigned rank greater than or equal to the signed rank, then we convert the signed one to unsigned. So the assigned op is the cast. So cast location to the unsigned type, the signed up. Okay. So that is that case, right? The unsigned integer type has rank greater than or equal to the signed rank. That is the case. Then we convert to unsigned. Okay. Otherwise, the signed integer type can represent all the values of the unsigned one. Then the unsigned one is converted to the type of the input. So when can it represent all the values? So it can represent all the values. So signed can represent all the values of the unsigned one if the bit width, like if the size of the signed one is bigger than the one of the unsigned one, then we can represent all values. So in other words, we need like a bigger, strictly greater rank. So if the signed rank is bigger than the unsigned rank, since the rank is the number of bits, this compares the value range. So if we can, like if that is the case, then we can definitely represent all unsigned values into one because we're having at least one bit more, which is enough. Okay, and then what we're doing in that case is we convert them to the unsigned. So the unsigned op gets the conversion. So essentially this one got flipped. So unsigned op converted to signed. Okay. Otherwise, both operands are converted to the unsigned integer type corresponding to the type of the operand, right? Otherwise, we're doing like need to do like a make signed. Okay, so we need an API for that. Make signed. Alright, so we get like similar to this. Make, right? We want make unsigned, right? We want to convert to the unsigned integer. Okay, make unsigned. So type make unsigned. Same, like similar deal right here. So if it's not a built-in type, we return null pointer. If it's signed int, we return built-in type uint. If it's this one, then we return the type unchained. And if it's void, then we return null pointer. This gives us a const type. This gives us a const type. Okay. So now we can convert the type to this unsigned type, which we are using right here. So in the last case, the target type is now the unsigned version. We will make unsigned. So as types create build. So we return the unsigned type from the target type, from the signed type. Okay, and then we will need to convert them. Okay, so signed up state as create cast expression log target type signed up, and then the unsigned up does the same deal. That is what I was worried about. So when you actually need to do like a const cast here to figure out how to remove the const cast. Unused. Okay. So for example, now we're doing like a binary op, arithmetic op right here. So essentially, like for all kinds of arithmetic expressions, we're doing like here. We're doing the arithmetic expression. So we're first checking whether it's a valid type. And if it is a valid type, then we can do the usual arithmetic conversions on them. Because this actually will always succeed. So the left and right. So the conversion can never fail at that point. And I believe that should be it to get this to work. Yeah, it worked. So those are the conversions here. And then I'm guessing we're also doing them. So let's just go to the standard and see where we do them. So usual arithmetic conversions. Usual arithmetic conversions. Doing integer promotions on shift. We don't worry about those. Okay. Relational operators. Usual arithmetic conversions. Quality operators. Usual arithmetic conversions. Okay, so comparison does usual arithmetic conversions. Usual arithmetic conversions. State, location, left, right. The bitwise AND operator. Usual arithmetic conversions. Where do I handle the bitwise operators? Oh, right, I'm doing them here in arithmetic. So bitwise AND does usual arithmetic conversion, bitwise OR does usual arithmetic conversions. Yeah, it's both ORs does usually, but the shift one does not, which is interesting, but okay. So I actually only need to do the if up shift left and shift right, then we're doing the usual arithmetic conversions. What about logical AND and logical OR? That does not do any conversions. Right, it does a comparison, right? Makes sense. So no conversions here. Conditional operator does comparison, and then it does right, usual arithmetic conversions on the result. Okay, so here we're doing usual arithmetic conversions on the result. Right here. So if we're having arithmetic types, arithmetic false type, then we do the usual arithmetic conversions. State log if true if right, if false. Okay. And the comma operator does no conversions at all. Okay, so I believe right, what then, like, sequence doesn't care about that. So what have to be scalar. Okay. And that should be conversions. Okay. So let's fix the bugs that we introduced earlier. But for now, this one works perfectly fine. Okay. Implement usual arithmetic conversions. Okay, and then we've broken a bunch of tests earlier when we added the cast expression. Because essentially, every time we have a parenthesized expression, this is now passed as if it attempts to parse the cast. So I need to constrain the parser. That parses a type name. So we need to have like a keyword type specifier. Right. Okay. So when we do the cast expression right here, we add a simple look ahead condition that we want an open parenthesis followed by white space followed by a type specifier, and only then do we consider that. Do I define white space somewhere? Probably don't. Okay, let's actually, yeah. Okay, so white space. Cast. Okay. And so now it will only attempt to do a cast when we have something that looks like a type. Condition in the operator. Really, the condition must be literal. That is so annoying. That is... Okay. That is really annoying. Okay. I'm actually out of time. So I have something coming up. So I have to end the stream here. This is the solution to the parsing problem. It's just not supported by Lexi. So we'll fix Lexi of grammar. And then next week, now that we have conversions, we can start adding more integer types. So thanks for stopping by, and until then.